Welcome to the mysteries of the universe, a world beyond our imagination where stars are born, galaxies collide, and nebulas light up the darkness. Humanity has looked up to the stars in awe and wonder for centuries. We have explored the outer reaches of our solar system, but there is still so much to discover. From the ancient astronomers who studied the stars to modern space telescopes that can capture the most distant and faintest objects, human curiosity about the cosmos has never wavered. In this documentary, we will journey deep into space to uncover the secrets hidden within the stars, galaxies, and nebulas that make up our universe. We will delve into the birth and death of stars, the formation and collision of galaxies, and the breathtaking beauty of nebulas. We will look at the new research and scientific discoveries that have helped us learn more about the universe and given us new questions and mysteries to solve. We will look at the birth of a star, starting from the dense cloud of gas and dust known as a nebula, where gravity causes the material to collapse and heat up, eventually forming a protostar. As the protostar continues to collapse and heat up, nuclear fusion begins, creating the intense heat and light we see in a star. We will also explore the different stars, from small red dwarfs to massive and luminous blue giants, and their impact on the cosmos. The universe is also home to countless galaxies, each with billions of stars and a vast range of structures, from spiral galaxies with their elegant arms to elliptical galaxies that appear featureless. We will look at how galaxies start, change, and interact over time, and how mysterious dark matter and dark energy are essential to how galaxies start and change. We will also inspect the beauty of nebulas, the vast clouds of gas and dust in space. From the iconic Orion Nebula to the stunning Eagle Nebula, we will explore the different nebulas and their role in the birth and death of stars. We will also delve into the mysteries of planetary nebulas, the glowing clouds of gas and dust created when a star reaches the end of its life. Finally, we will look at the current and future space missions that aim to explore the mysteries of the universe and the technologies that allow us to study the stars, galaxies, and nebulas in greater detail. Join us as we uncover the universe's secrets and discover just how much we have yet to learn about the world around us. From the birth of a star to the collision of galaxies, from the stunning beauty of nebulas to the mysterious dark matter and dark energy, we will explore the mysteries of the universe and find out how much we still don't know about it. In the stellar nurseries of the cosmos, stars are born. They live for eons. Then do they die? Why do some live longer than others? Well, it depends on how big they become and precisely what combination of elements they are composed of. Somewhere between here and the edge of the universe lies the answer. Nearly 4,000 light-years away, further luminous clouds suspended in space encircle what was once a star like our Sun. All that's left of it are these brightly colored gases. Elements formed by nuclear fusion deep inside the star are released into space upon its death. Green and violet hydrogen and helium, the raw materials of the universe. Red and blue nitrogen and oxygen are the building blocks of life on Earth, the oxygen in our lungs and the nitrogen in our DNA. We are all produced by nuclear fusion. Stars like this had to die so that we could live. Stellar nuclear waste in the stars died long before the Earth was even born. Our fantastic family tree begins here. At its heart, the ghost of a star. It's a white dwarf, white, hot, and small. However, in the dying moments of the star, its atoms fused and squeezed together, resulting in a white dwarf so dense that a teaspoon of it would weigh 1 ton. It's a chilling premonition of our sun's fate. 6 billion years from now, it'll become a white dwarf. Its death will herald the end of life on Earth. It makes you wonder how many other worlds have come and gone. Untold stories and celestial evidence are gone for good, but the most incredible story of them all is still to be told. We must go back through time to the very first chapter to tell the story of how the universe began, the scattered remains of a dead star. A nebula, the Crab Nebula. The Crab Nebula, also known as Messier 1 or M1, is a supernova remnant in the constellation Taurus. The nebula gets its name from its appearance, which resembles a crab when viewed through a telescope. It is one of the most studied and well-known nebulas in the sky. The Crab Nebula is the remnant of a supernova that occurred in 1054 AD. The supernova was likely caused by the collapse of the core of a massive star, leading to an explosion that expelled material out into space at high speeds. This explosion was so bright that it was visible in daylight and was recorded by Chinese and Korean astronomers. The nebula is approximately 6,500 light-years away from Earth and spans about 11 light-years across. It is a mixture of different materials, including glowing gas, dust, and the remains of the exploded star. The gas and dust are lit up by the intense radiation from the supernova's remnant, known as a neutron star. This neutron star is incredibly dense, with a mass around 1.4 times that of the Sun, but it is only about 20 kilometers in diameter. One of the Crab Nebula's most striking features is its gaseous filamentary structure. These filaments are created by intense radiation and magnetic fields within the nebula. The radiation causes the gas to heat up and emit light, while the magnetic fields shape the gas into filaments. The glowing gas is arranged in long, thin tendrils that twist and turn throughout the nebula. The Crab Nebula is known for its high-energy emissions, including X-rays and gamma rays. These emissions are produced by the intense radiation from the neutron star and by the acceleration of particles within the nebula's magnetic fields. The Crab Nebula is also a vital source of radio waves and infrared radiation and a source of cosmic rays, which are high-energy particles believed to be sped up by the neutron star's magnetic field. The Crab Nebula is also essential in astronomy, as it has proved critical insights into supernovae, neutron stars' properties, and matter's behavior under extreme conditions. It's also one of the most energetic objects in our galaxy and an intense source of high-energy radiation. Studies of the Crab Nebula have led to the development of new technologies and techniques used to study other astronomical objects. The Crab Nebula is a spectacular example of a supernova remnant and one of the most studied objects in the sky. It offers information about supernovae, neutron stars' properties, and matter's behavior under extreme conditions. Its intricate filaments, energetic emissions, and intense radiation make it a captivating astronomical object that continues to attract the attention of scientists and amateur astronomers alike. Einstein's theory of relativity has profoundly affected the field of astronomy and cosmology. From the bending of light around massive objects to the existence of black holes and gravitational waves and the properties of the early universe, the theory of relativity has led to many breakthroughs and discoveries. The continued study and application of the theory of relativity in astronomy and cosmology will lead to a deeper understanding of the universe and help us unlock the mysteries of the cosmos. We've worked for a century to test it. Einstein's relativity is holding up. Scientists are unraveling the Big Bang itself and asking new questions about our cosmos. We are still not entirely sure how supermassive black holes form, but we've been able to detect that they exist in almost every galaxy. New instruments are confirming old theories. It has taken us about 50 years to make a device that detects gravitational waves, shedding light on the fate of the universe. We may be sailing off on an infinite journey of expansion with each piece of the puzzle. The mysteries deepen. We must find the boundaries of our ignorance, and that's a fascinating place to be as a scientist. Humankind has forever sought to understand the forces that govern the heavens and the world around us. After William Herschel discovered Uranus in 1781, astronomers noted its curious path across the sky, employing Newton's version of gravity. The planet's motion was influenced by a distant body. European astronomers and mathematicians got together and calculated that if there was an existing planet outside of Uranus, this would explain these funny movements. Two astronomers independently calculated the hypothetical planet's location in the night sky. A third trained his telescope toward that position. Collectively, they discovered Neptune. But there was one planet that refused to play by Newton's rules: Mercury. Tracing Mercury's orbits, its closest point to the Sun, its perihelion, moves ever so slightly every year. The phenomenon is known as precession. Mercury's orbit never quite fit correctly with the classical model. It could not be explained by Newton's law of gravity. After we had observed it and seen the perihelion advance, perturbing Mercury's orbit, the mystery planet was christened Vulcan after the Roman god of the forge. While some hunted for Vulcan, others sought a new mathematical theory to explain Mercury's strange behavior. One hypothesis is that there had to be another planet even closer to the Sun. In 1915, a German physicist presented a new take on gravity. Einstein's relativity absolutely transformed the way we think about the universe. Step out of this classical world of gravitation and turn that entirely upside down and come up with a mathematical formula that is quite simple. General relativity treats space as deformable mass from a grain of sand to the entire Earth that bends space, and all natural bodies moving through the universe will follow these curves. The Sun doesn't pull on the Earth. The Sun sits at the bottom of a gravitational well, and the Earth falls around it, traveling fast enough that it doesn't spiral inward. We saw a sweeping away of the old and the arrival of a new paradigm in relativity. Applying the novel equations of general relativity, Mercury's quizzical orbit was finally explained, and its precession accounted for. Vulcan was no longer necessary. However, Einstein's theory would need further demonstration to supplant Newton's work, which had reigned supreme for over 200 years. Einstein had predicted a massive object would bend the way light passed through space. An upcoming solar eclipse would have darkened the southern Atlantic on May 29, 1919. A team of astronomers led by Arthur Eddington seized the opportunity to test Einstein's theory. The Eddington mission in 1919 was to measure the deflection of a star's light as it passed close to the Sun. If Einstein was correct, a group of stars would appear in a slightly original part of the sky. Their light was perturbed by the Sun's gravity as it passed in front. In 1919, the eclipse was particular because this eclipse happened projected against the background of the so-called Hyades star cluster, a small concentration of stars that were the best-studied stars to date. A first observation base was established in Brazil, and Eddington positioned himself on an island off the coast of West Africa. The Moon's shadow charged across the Atlantic. Each station only had minutes to capture the eclipse on photographic plates. Returning to England, both teams announced their findings. Einstein was right. This experiment was a huge success, and the differences in the positions proved that Einstein's predictions were correct. Scientists have continued putting general relativity to the test. It keeps passing. For several centuries, we've worked with Newton's gravity. Then came Einstein with relativity, showing that Newton's gravity doesn't work well in certain extreme situations. Einstein could explain everything we see even to this day. We still need to go against his theories of gravity. Now, is Einstein's relativity the definitive answer? We've worked for a century to test it. Einstein's relativity is holding up precisely. Astonishing. It all came back to a simple desire to understand and have a complete picture of our universe. While we can still use Newtonian mechanics in our day-to-day lives, Einstein's revolutionary notion of gravity is required to understand the universe. We must look for extreme densities, temperatures, and highly dynamic environments. That's where we can refine our ultimate theory of gravity. To study the heavens, astronomers capture light in telescopes. That light is composed of a spectrum of colors. We can understand the fundamental makeup and dynamics of something by taking its light and splitting it up into its component colors. Unique to each object, this combination of colors represents the chemical fingerprints of astronomical phenomena. But to understand how a star or a planet could have such a fingerprint, scientists need to surpass the classical understanding of the universe. They needed to reconceptualize the very concept of matter. The ancient Greeks envisioned the atom as indivisible, the most fundamental building block of substance. In the 19th century, scientists discovered it was far more complex. As our ways of studying materials advanced in the past 200 years, the structure of the atom is no longer just one homogeneous thing, which is the most minor thing in the world. The atom was instead shown to be composed of several components, a nucleus where most of the mass was contained with an electron that would orbit around. Quantum physics. In 1913, the Danish physicist Niels Bohr introduced his atom model. The model relied on an alternative explanation of reality recently developed. But according to classical Newtonian physics, the electrons in a planetary model would spiral down toward the nucleus, destroying every atom in existence. Quantum physics is the idea that nature is divided into discrete but very much differentiated bits. It's trying to explain the very most minor scales of the universe. The tiny bits of atoms and how they behave, the weirdness and behavior of chemicals, and basically every tiny thing in our universe. In this re-envisioned universe, electrons are forced to orbit around their nucleus at precise distances like rungs on an unevenly spaced ladder. The exact colors of light an atom can absorb or emit are determined by the size of those rungs. Each element has its own arrangement. We have a unique challenge in visualizing and explaining the quantum world. For decades, astronomers had been cataloging stars based on the missing colors in their rainbow of light, called spectra, and matching them to certain elements. If we look at a spectrum and we see specific wavelengths missing, we can tell which element in the star absorbed that light. Scientists could use spectra to identify chemical compounds throughout the cosmos. The ghosts of unimaginably distant objects like quasars and pulsars can tell their stories by manipulating the light they emit. In the 1920s, quantum physics developed. The particles within an atom were revealed to also act like waves. The electron is not in a position around the atom. It is rather spread out. There is a cloud of probable locations. The universe became uncertain, which helped solve a long-standing mystery of how our sun could shine. Under classical physics, hydrogen nuclei in our Sun's core cannot get close enough for fusion to occur. It simply isn't hot enough. But under quantum physics, hydrogen clouds can. The chance of fusion is astronomically tiny, but it's enough. Combined, the theories of relativity and quantum physics have allowed us to explain the intricacies of the universe, but employed in tandem, they provided no answers. These are two theories of the way things behave which are mutually exclusive. They don't sit together, yet they both work very well. When we try to describe big things with quantum mechanics, it makes no sense. When we try to describe tiny things with general relativity, that doesn't work either. Gravity, as we currently understand it, cannot operate within a quantum realm. There must be a theory out there that we still need to grasp. It could be a new physical law. It modifies these laws and something else. Reality, as we know it, was born. With a unified theory, we'll be able to truly comprehend the beginnings of our universe. 13.8 billion years ago, all of the matter in our universe originates from a single point. That's the Big Bang. An infinitesimal spark became an infinite cosmos. It's not so much an explosion into space, it's an explosion of space itself. As the universe grew unfathomable, stars shone and galaxies coalesced. Modern technology allows us to observe many of these moments, but only some of the earliest points of our universe's history. As we turn back the clock, a cosmic barrier rises 380,000 years after the Big Bang. Our universe was hot and dense for the first few 100,000 years before that point. Atoms were ionized and they were plasma. Any radiation a particle emitted would immediately be absorbed by another, and it acted like a fog. There was no way for the light to travel. When the universe expanded and cooled sufficiently, radiation could start flowing freely. The atoms recombine, the fog clears, and the light travels to us and has traveled towards us essentially unimpeded since that moment. The oldest light is known as the cosmic microwave background. It wasn't discovered with our eyes but our ears. In 1964, two astronomers at Bell Laboratories were testing their radio equipment, but something was interfering with the signal. Maybe it was caused by something in the Earth's atmosphere, and they spent a long time trying to remove it from their data. They went to great lengths to account for and remove the effects of this static. They thought it was actually bird poop they were looking at and had to clean it out because pigeons nested in their telescope. They didn't call it bird poo in the paper that they published. They called it a white dielectric material. They did not know what was causing it. It wasn't clearly coming from anything we knew, and it was called little green men for quite a while because what else could it be? They would talk to a physicist, Hans Peter, who had some understanding of what might be going on, and they could ultimately conclude that the static that they were hearing was actually the cosmic microwave background, the relic radiation from the Big Bang. Over the decades, space-based observatories have mapped this signal, which exists everywhere in the sky with eerie uniformity. One of the earliest measurements was made by a satellite observatory called COBE, the Cosmic Background Explorer. It made an incredibly famous measurement of the temperature of the microwave background. It is one of the most precise, pristine measurements in all astronomy, maybe in all science. Our universe had a beginning and has been expanding ever since. The remnant heat of the Big Bang was predicted to be a few degrees above the coldest possible temperature, roughly minus 270 degrees Celsius. The COBE mission confirmed that prediction. The cosmic microwave background is constant all over. The universe implies it was all produced in the same place, which enabled the cosmic microwave background experiments to confirm the Big Bang theory. Following COBE, further missions exposed hidden structures of an infant universe where gravity could act to form stars, galaxies, and the Earth itself. However, all that we've learned from the cosmic microwave background only takes us so far back from the 380,000-year barrier earlier, and we have to rely on scientific theories and models. We can use Einstein's relativity to work our way back in time. Quantum physics also describes how the particles interact in this universe, which becomes tiny and concentrated. But the theory fails us at the earliest moments, when all cosmic energy was contained in a nearly infinitesimal point. A tiny fraction of a microsecond away from the Big Bang, we don't have a theory that works all the way into this extreme regime. Our equations actually break down. Beyond our origins, physics is broken in other places. The most extreme objects in our universe are invisible. A black hole is a region of spacetime which is so dense and has such strong curvature that nothing, including light, can escape from it. It's what happens at the end of the lifetime of a very massive star. For the most prominent stars, life ultimately ends with a gravitational implosion, a supernova. The mass left behind won't have any fuel to sustain it. It all crumbles together into an infinitesimal point, a black hole. There is no surface, only an edge past which you could never retreat, trapped for eternity. The idea of a hole is very apt. Looking up into the universe you had just left would be an ever-narrowing well of light above you. The notion emerged from Einstein's equations. However, black holes spent decades as mere mathematical oddities, not real-world phenomena. In 1971, astronomers identified an intense X-ray source dubbed Cygnus X1. It lined up almost perfectly with a known star, but the star could not generate those X-rays. By 1973, a consensus had been reached. The star was orbiting a black hole. The following year, a source of intense radio waves was identified in the heart of the Milky Way. The phenomenon of Sagittarius, a star, was best explained by a black hole. The radio waves are emitted by matter in a disk surrounding the black hole, spiraling downward. As it gets ever closer to the black hole, its orbital speed increases and eventually becomes close to the speed of light. In doing so, it's constantly bumping, jostling against its neighbors. It is a tremendous amount of warmth, heat, and light. Even though astronomers couldn't figure out what Sagittarius was as a star, they could look at its neighbors. We've been able to measure its presence, and we've been able to measure its mass, not because we can see it directly, but because we can measure its gravitational influence on the stars that orbit very close to it. The black hole at the center of our galaxy has a mass roughly 4 million times that of our Sun. We call a particular breed of black hole the supermassive black hole. Most galaxies, if not all, contain a supermassive black hole at their very centers. So most of the most enormous galaxies have black holes with 20 or 30 billion times the mass of the Sun, which is astonishing. We're still not entirely sure how supermassive black holes form, but we've detected that they exist in almost every galaxy. While indirect data suggested black holes were a part of our reality, capturing visual evidence seemed nearly impossible. Because radio wavelengths are the longest among many lights, they require much larger telescopes to capture. To image a supermassive black hole in another galaxy would require a radio telescope as giant as our planet. We'd love to build a telescope the size of the Earth, but we need help. Humanity accepted the challenge. An international collaboration of organizations and observatories combined their efforts to birth the Event Horizon Telescope. We use several telescopes sited around the world, and we use them as a team to make a perfect picture. You have large radio telescopes in varying places on the planet. You can combine those signals and simulate a radio dish the physical size of those separations. The Event Horizon Telescope set its sights on the center of Messier 87, a galaxy 55 million light-years from Earth. Beginning with 3 observatories in 2009 and expanding to 8 by 2017, the data collected by each telescope was fed into a supercomputer. The stories from each telescope are put together in this computer to make one incredible, clear, and revealing picture. When the images were finally processed, they revealed the shadow of the black hole rather than the black hole itself, measuring 100 billion kilometers in diameter. Nestled within a supermassive black hole 6.5 billion times the size of our Sun, we see a region where time stops. This is a very different part of the universe we're seeing for the first time. While scientists cannot explain the intricacies of black holes until we find a theory that unites physics, they have developed new methods to study them. According to general relativity, light waves are not the only ripples traversing the cosmos. Space itself can also ripple. Gravitational waves are caused by mass speeding up through space. Einstein first predicted gravitational waves in 1916, but the size of these waves was going to be so small that he never thought they would be detected. Only the most extreme events in the universe create measurable gravitational waves. When it got to where black holes were no longer ridiculed, the physicists started saying, maybe we can seriously think about building a detector now. We would need a lab to isolate space-time distortions smaller than an atom. It has taken about 50 years to build an instrument capable of registering gravitational waves, the shaking of space itself. In 2002, the Laser Interferometer Gravitational Wave Observatory, better known as LIGOS, began searching for evidence to support Einstein's proposition. We detect gravitational waves using instruments called interferometers. They are shaped like an L. We shine a laser from the center of the L down the 2 arms. After traveling 4 kilometers down either arm, the laser light strikes a mirror and returns. The principle is that if a gravitational wave comes from out in space and passes into the detector, it will stretch one arm and then the other, and we'll see this in the interference pattern of the laser beams when recombining. To ensure a signal is genuine, Legault built 2 detectors on opposite sides of the United States. Both stations were silent for years, but following an extensive refit, a signal was detected. When 2 black holes orbit around each other, they lose energy by the emission of gravitational waves. They enter a death spiral, orbiting faster until they collide. Einstein's theory dictated the event, and both LIGO's signals matched it. We detected the merger of 2 black holes, a collision of 1.3 billion years old. Once we had the first one, it became apparent that we would get more of them as we increased the detector's sensitivity. Legault witnessed another type of collision 2 years later. The second really major detection for LIGOs was binary neutron-star collision. When they collide, they give off all kinds of signals. Unlike a black hole merger, a neutron-star collision could be witnessed with a gravitational wave detector and optical telescopes. We were fortunate to localize the area in the sky for that signal to a tiny patch. We sent it out to the astronomers, creating an unprecedented avalanche of telescopes and satellites around the world, redirecting their observing programs that had a flow-on effect. Everybody could imagine it on radio, X-ray, and so on. And this gave us an enormous amount of physics that we didn't previously have. Humanity has entered a multi-messenger astronomy era, studying the same object using a combination of information sources and employing multiple phenomena to confirm, enhance, or contradict our previous notions of the universe. Whether radio waves or light, you can see their eyes' X-rays. If we're wrong about our view of light, everything in our universe is essentially wrong. It requires a light particle that travels through space, so gravitational waves offer an independent way of measuring the universe. It gives you a holistic picture of what is happening out there. The more messengers you can use, the better informed you are about how the universe works. Messengers that come from traditional ways of viewing the sky, they come from particles using all of the information. That is how astronomy progresses, and extensive collaborations are formed between specialists in different disciplines. It's a bright future for astronomy. More powerful gravitational wave detectors could reveal the earliest moments in the cosmos. The oldest gravitational waves would reveal our history until a tiny fraction of a second after the universe's creation, while the oldest light takes us no further than 380,000 years after the Big Bang. I look forward to that with great interest, because it may turn out that we've got it all wrong. And when we look at the gravitational waves, they tell us a different story from what we expect. In the 1920s, humanity realized that our Milky Way galaxy was just 1 million and billions of light-years away. Some galaxies were moving so fast that they should have broken free. Other galaxies clustered together and slowly rotated around one another. A decade later, Swiss astronomer Fritz Zwicky had a mystery. He had been observing the Coma Cluster, a group of over 1,000 galaxies stretching 10 million light-years across. Given their collective mass and gravitational influence, gravity from the galaxies that we see is not enough. There must be more gravity to allow the cluster to hold together. Otherwise, the galaxies would have whizzed off into space and we wouldn't have clusters anymore. Just as all the bodies in our solar system orbit a central point, all the stellar systems, gas and dust in a galaxy rotate around the galactic core. In the 1960s, Vera Rubin and Kent Ford began charting these rotation rates, measuring how fast material within a galaxy spun relative to its distance from the center. Several decades later, studies of individual galaxies posed the same problem. Spinning matter in our universe operates under a principle known as the conservation of angular momentum. The total amount of mass and the distribution of that mass dictate how quickly an object will rotate. You could do this right now. You could spin around in your gesture and test it that as you move your arms out you slow down, and as you move your arms and speed up. Exactly. Planets in our solar system are rotating, based on gravity, the Sun's mass, and the planets' masses. But instead of slowing down at the outer edge of a galaxy, Rubin noticed these stars moved as fast as those much closer in. Vera Rubin showed that the stars in a galaxy are not rotating like the planets in our solar system. They're rotating as if there's much more matter than we can see in the galaxy. And so, either our laws of physics are wrong, but they work in every other case, or there's another type of mass that we've never discovered. Zwicky called this an invisible matter. We know it today as dark matter. We call it dark matter because it doesn't emit light or absorb light, so the only way it interacts with other materials is via gravity. Dark matter forms massive structures across the universe, existing as gravitational scaffolding. We see its effects in photographs looking at galaxy clusters. The dark matter will distort the images of any galaxies behind it, This effect is known as gravitational lensing. Gravitational lensing is an excellent effect in the universe, where if you have a massive object, the light will get bent around just like a magnifying glass, or like a refracting telescope that magnifies the light of the background galaxy and distorts it. After accounting for the lensing caused by ordinary matter, astronomers can map the distribution and concentration of dark matter. It appears 5 times more abundant at current measurements than all visible matter. There is a lot of mass in the universe that we cannot see with our eyes, that doesn't emit light but interacts in every other way we measure it. Scientists continue to hunt for an explanation for dark matter. Dark matter could be made of particles that we have yet to discover, and we're looking in places like the Large Hadron Collider, smashing high-energy particles to spew out these excellent particles we have yet to discover. Neutrinos, the smallest and least active particles known to physics, could be used to look for one type of dark matter. If dark matter is another type of particle that we have yet to see, when dark matter collides with itself, it should emit neutrinos that can travel through space, which we can see here on Earth and measure and collect in a laboratory. So, neutrinos are the awkward cousin in the family. Neutrinos are in the same family of subatomic particles as electrons, but they have no charge. They are ghosts from space interacting with matter in such a strange way that trillions of them are moving through your body. There are some intriguing suggestions from deep underground experiments where you build particle physics detectors, seeing things that can easily pass through the Earth. We go to the bottom of mines or underneath mountains to use the rock above as a shield to have a better chance of seeing this rare collision with our detector. The internationally funded IceCube experiment at the South Pole is the largest neutrino detector in the world, a cubic kilometer in size, buried over 2 kilometers below the Antarctic ice, turning 1 billion tons of naturally frozen water into its own personal neutrino catcher. Across 2 years, IceCube indirectly detected 28 neutrinos. However, none were attributed to dark matter. The experiments have given some weird hints that we might get close to finding whatever particle makes up dark matter. Meanwhile, NASA's Fermi Space Telescope hunts for the signatures of dark matter from low Earth orbit. That type of dark matter forms antimatter, and matter can form and then collide together and annihilate themselves. Such an annihilation would create gamma radiation, which Fermi detects. So far, it hasn't detected them, but it's getting very close now. We're narrowing the search field. Scientists will only find solid evidence once scientists find solid evidence. The scarcity of detections limits the possibilities for what dark matter might be. Another possibility is that dark matter could not exist. We may have gotten the maths wrong, and that's even more intriguing and even more worrying. However, another search for the invisible leads to an even larger mystery. Astronomer Edwin Hubble revealed to the world that our galaxy was just one of the billions in 1924. Less than a decade later, he announced another revelation. The universe was not constant, it was expanding, and the expansion set forth that our origins would slow under the power of gravity. Over the decades, astronomers settled upon the Big Bang theory. The expansion of the universe originated in the Big Bang. But everybody thought that because the universe is full of matter, galaxies would slow down the expansion by their mutual gravitational pull. Eventually, the universe would begin to collapse. The race was on to calculate when. People were trying to set out how fast the universe was slowing down. When was the universe going to stop and collapse back on itself? In the 1990s, 2 international teams began measuring expansion using some of the brightest phenomena known in the universe, Type 1a supernovae. the teams compared the age of particular supernovae with how quickly they were moving away from Earth. By 1997, the teams had collected a wealth of data stretching back to half the age of the cosmos. The following year, they went public with their conclusions, so defying the known laws of physics. The universe is not slowing down in its expansion, it is speeding up, and it seemed for a while that this must be a fluke of the measurements. Something needs to be fixed with the observations, matching the exact opposite answer that you're told to find. That is a big test of your scientific process. In two independent teams found the same thing. We now know that the observations are absolutely secure. You can look at the universe and see the same phenomenon. At the turn of the millennium, a supernova hidden in the Hubble Space Telescope was dubbed dark energy in June 1998. Data added to the universe's complexities 10 billion light-years from Earth. It was the oldest found up to that point. It revealed that billions of years ago, the universe's expansion was as physics had initially predicted. Dark energy was weaker than it is today, and before our Sun and all its planets were born, dark energy began winning a cosmic tug-of-war, pushing galaxies apart with more strength than gravity was pulling them in. The mystery of dark energy tantalizes cosmologists. Well, the most exciting breakthrough in cosmology is the discovery that the universe is speeding up. So what's causing it? Particle physics says that there is energy in the vacuum itself, and in fact, if that had been the dark energy, the universe would have ripped itself apart, probably within the first second of its existence. It's often been described as the worst prediction or mismatch in history. The European Space Agency's Planck telescope hunted for pieces of the dark energy puzzle by imaging the cosmic microwave background, the oldest obtainable light. With this data in hand, astronomers calculated the exact composition of the universe. Only 5% of the universe is known. Dark energy comprises roughly 68% of all there is. Dark matter makes up another 27%. It is a tangible substance or a visible light. But it's even worse than that. Most atoms in the universe will never even fall into a galaxy and reveal themselves. Bits that have made it into galaxies. That's basically 1% of the universe. But, so far as we're aware, we're the only part of the universe that has looked at it and wondered what a bit of this universe we are. To understand dark energy is to know the ultimate fate of the universe. Based on what we know about dark energy, we might set sail on an endless journey of expansion, and the universe would last forever. More and more and more, every star will, at some point, disappear, be infinitely far away from every other star. Every particle will decay eventually. According to Einstein's relativity, that would be a runaway process where the expansion speeds up forever. The universe will end as a cold, dark, lonely place. Better to be alive now than in 40 billion years. Missions to probe the mysteries of dark energy are already in motion. There are different ways of measuring dark energy. We can see exploding stars. We can use clusters of galaxies. We can use held light bins around some galaxies. At the Vera Rubin Observatory in Chile, astronomers embark on a decade-long venture to map the sky deeper than ever, capturing 20 terabytes of data each night and cataloging 37 billion stars and galaxies. And we use those results as independent cross-checks. The other probes, and we're trying to pinpoint that intersection of what dark energy could be now, which tells us what dark energy actually is. Reality's greatest mystery is a test of patience. We have defined the boundaries of our ignorance, and that's a fascinating place to be as a scientist, for something that didn't exist from 1997 to 20 years later. Having hundreds of people worldwide trying to discover it shows how big of a question it is to understand our universe's nature, the beginning of our universe, and the future of our universe. Humanity's perception of reality is ever evolving. Our view of the universe is dramatically different. 30 years ago, 50 years ago, and 7,100 years ago. And it's incredible to think about how much we've learned about the universe in the last 10 years. The vast unknown reaches of the cosmos are begging to be explored. We must find out if our picture of the universe is wrong. 95% of the universe comprises entirely mysterious dark matter and dark energy. We're still figuring out what makes this up. The study of the universe, it's a never-ending series of amazing discoveries about what is possible. It challenges our notions of who we are, where we come from, where we'll go, and how precious our planet is. It affects humanity on practically every level, and that's why I find it endlessly inspirational. Our quest for answers is an essential part of what makes us human. The universe created planets, life, and people who can ask all these questions. That's just marvelous. We hope to one day understand our place. We are just a tiny fraction of the universe, but so far as we're aware, who is the only bit of the universe that has looked at it and wondered what a bit of this universe we are. In an age of planetary exploration, NASA's Phoenix lander descended to the Martian surface. Frozen water. The red planet had remnants of water buried beneath the surface. It will soon be discovered as a treasure. Earth was no longer the only terrestrial world with the vital ingredient to life as we know it. Throughout history, we've observed our planetary neighbors in the sky. Human beings have looked up to the stars for as long as possible. Probes and landers have ventured to other terrestrial worlds, Mercury, Venus, and Mars. All new areas in astrodynamics had to be invented to do this. Each journey revealed secrets of our solar system. We actually learned a lot about Earth by looking at other planets, and this brought us closer to the possibility of alien life. There was more and more of this history of a watery past on Mars and an environment that could have even been suitable for life at one time. Every mission has paved another stone on our road to an off-world colony. The moment we step foot on an alien world, we have forever changed it. 4.6 billion years ago, our solar system was merely a giant cloud of gas and sprinkles of dust formed by ancient stars. But under the power of gravity, that cloud started collapsing, spinning ever faster and flattening into a disk. Solar systems are always flat disks because they flatten out when things rotate in space. A dense sphere of gas collected in the center. At its core, under intense heat and pressure, hydrogen began undergoing transmutation and nuclear fusion, releasing an explosion of energy that continues to this day. In this new solar system, tiny grains of dust began sticking together. A few grew massive enough that their own gravity crushed them into spheres. The Sun was born over 100 million years. The planets were leftovers from the Sun's formation, and slowly over time they accumulated more and more material from the disk around the Sun. Our star's radiation blew away lighter gases like hydrogen and helium from the inner system. Ice could not form, and 4 rocky planets arose: Mercury, Venus, Earth, and Mars. We talk about the terrestrial planets. These are the inner worlds, the rocky bodies. While all started with a similar evolutionary process, each reached a unique fate. If you learn more about these terrestrial planets, you will learn more about our history, and space exploration is about learning about ourselves. The most visible planet in the sky, Venus, is our immediate neighbor in the solar system at the closest possible distance of 38 million kilometers. The planet has shaped our understanding of our place in the universe. Humanity's comprehension of the solar system has expanded over the centuries. In the 1600s, Galileo Galilei observed Venus's phases, helping to confirm the Copernican notion that the planets orbited the Sun instead of the Earth. But Venus's opaque cloud tops stirred speculation that habitable swamps or even oceans awaited below. Answers seemed within reach with the development of the first robotic visitor to another planet. But any craft venturing beyond Earth's protective bubble would endure the dangers of interplanetary space. A probe in space can be subjected to conditions far beyond anything we'll see on Earth. We're lucky that Earth's atmosphere protects us from extreme temperatures or radiation from the Sun. The closer you get to the Sun, the more radiation you have when there's a solar flare. If the Sun does a hiccup, you can get powerful streams of charged particles that can knock out a spacecraft's electronics. Designing probes for the space environment requires careful consideration of radiation, heat, pressure, and temperature changes because it's straightforward to, within the life of a mission, to experience very high shifts in temperature. In the early 1960s, NASA began developing spacecraft to explore the solar system. The Mariner program consisted of 10 probes destined for the terrestrial planets that were launched over a decade. They activated the Destroy command. After Mariner 1 failed, only 5 minutes after launch, attention was drawn to its successor as our first emissary to Venus, Mariner 2, a sophisticated uncrewed spacecraft tasked with gathering data on the planet. The second Mariner blasted off from Cape Canaveral on August 27, 1962. However, piloting a craft toward the center of our solar system came with a unique challenge. It's actually challenging to get to the inner planets. They whiz right past. It would be best if you slowed them down. The probe would gain so much kinetic energy. So, a spacecraft leaving the Earth's surface relative to the Sun has a very high velocity, and it's got to lose that velocity to reach Venus. 4 months after leaving Earth, Mariner 2 passed Venus by becoming our first interplanetary traveler. Mariner 2 was the first successful flyby of anywhere in our solar system, gliding past Venus for the first time, peering into its shadowy world and detecting gases in its atmosphere. Mariner 2 revealed a thick, crushing blanket almost entirely composed of smothering carbon dioxide. Venus is an inhospitable place. We wouldn't want to live there. Sulfuric acid rains down from near hurricane-speed winds, except it can't reach the surface because it's so hot. Despite being a similar size to Earth, we had not found a twin, but the worst-case scenario of a runaway greenhouse, a buildup of heat-trapping gases that spiraled out of control. According to rising CO2 levels from volcanoes, heat causes more evaporation and clouds. Clouds trap heat. It's now insulated and boiling at this considerable temperature. Mariner 2 confirmed Venus spins on its axis opposite to the other planet's conventional direction. But that may only sometimes have been so. The accumulation of its thick atmosphere didn't just affect Venus's temperature and pressure. In the first couple of billion years after its formation, Venus rotated similarly to the other planets. And then, over the last few billion years, Venus has been slowing down, almost stopped, and rotated in the opposite direction. Venus is thicker, and the atmosphere may be to blame. The Sun's gravitational influence could have pulled on it with enough force to cause retrograde rotation. All we know is that there is something extraordinary in the history of Venus. It has an extraordinary atmosphere, and the two are connected. Hot on the trail of Mariner 2, the Soviets initiated the Venera program. The goal was to pass Venus by and touch its surface. During the Cold War, when the US aimed for the Moon, the USSR sent missions to Venus. It's the actual red planet. Early probes were crushed by the intense pressure before they even reached the planet's surface. Venus's environment was challenging as the first mission began to travel and collect closer data. Venera 7 made the first transmission from another planet's surface. The following probe's parachute failed, but it reached the surface intact. The probe survived for 23 minutes before succumbing to heat and pressure. The Venera program, run by the USSR, was an incredibly successful mission in the scientific exploration of our solar system. The probe measured surface temperatures of 475 degrees Celsius, and scientists inferred an atmospheric pressure 91 times that of Earth's at sea level. 5 years later, in 1975, Venera 9 returned the first image from the surface of another planet. A single black and white photograph exposes a rather mundane rocky surface. It was an almost impossible task to battle land probes on the surface of a world like that, but the Russians achieved it and sent back the first images of that world. And once that mission had been successful, it was possible to design future missions to adapt to what we now need. The Soviets continued the Venera program into the 1980s, sending back more images and data. Even today, those images help us form our understanding of that planet, even though we're only just looking at a few small areas. Rather than focus on a tiny area of Venus, NASA's next mission sought to map nearly all of its surface. On May 4, 1989, Magellan became the first deep space probe launched from a shuttle. The advantage of launching a probe such as Magellan from the shuttle rather than from a conventional rocket is that you have more control over how it sets off. The shuttle is controlled by people, so the instrument can be checked out safely before it is sent into space. That allows you to efficiently send the probe off without complex thrusting maneuvers or anything coming from the spacecraft itself. We started the elevation procedures for the deployment. We threw the switch and sent Magellan on its way. 4 months after leaving Earth, Magellan began transmitting radar images of the Venusian terrain. Magellan's spacecraft could use radar to penetrate through that blanket of cloud to look at a totally alien surface. It was a world covered in volcanoes and areas of lava flows. Venus's mapping quickly revealed that it is also active. Venus is volcanically active. It's seismically active. Processes are happening on the surface. The land is changing. The land is forming. Though some regions show geologic change and renewal, Venus's crust is hundreds of millions of years older than Earth's. Our neighboring alien world cannot recycle its rock as our planet does through the movement of tectonic plates. Magellan revealed the possibility that within 2 billion years of its history, Venus may once have been like Earth, with a liquid water ocean and habitable surface temperatures. Venus originally had an atmosphere similar to Earth, but over time the water boiled off because of the sun's radiation. Venus is closer to the sun than the Earth, so it receives more of the sun's light. As the sun ages, its luminosity grows, shining an ever more powerful light on the Earth. With humanity's addition of greenhouse gases into the atmosphere, our planet may one day reach a similar fate. Our Earth could go the same way. It really makes us think about how precious our environment is. There is a mystery about the origins of Venus that we want to understand to save ourselves in the future. It really is our Earth's evil twin, which was only revealed because of these robotic missions. The European Space Agency's Venus Express began orbiting the planet in 2006. One of the craft's more surprising discoveries was an uncharacteristically cold region high in the planet's atmosphere, where carbon dioxide could freeze into the snow. Dipping to -175 degrees Celsius, atmospheric layers like these entice astrobiologists. The atmosphere of Venus might be home to some life. It couldn't be anything like we think about here. As a world of so many extremes, a myriad of mysteries remain. I suspect Venus will keep its mysteries for longer, if only because it hides them so well. Named for the Roman god of messengers, travelers, and thieves, Mercury is the most minor planet in our solar system. At an average distance of 77 million kilometers from Earth, Mercury is the innermost world. Mercury is a tiny planet and very close to the Sun, and the Sun has a constant stream of very hot charged particles coming off. It is called the solar wind, which stripped away Mercury's atmosphere long ago, and it's creating a little helium atmosphere from the gases inside the rocks on the planet's surface. Mercury is a world of temperatures over 400 degrees Celsius during the day and -200 at night. Understanding this tiny world is crucial to the terrestrial planet's puzzle. The world itself is remarkably dense, like Earth. Mercury's interior has layers. However, Mercury's core contains far more of the planet's mass, 85% compared to Earth's 55%. If you think about what's underneath the ground of the Earth or Venus or Mars, if you strip away the atmosphere and the stuff on it, this is probably the core of what a planet looks like. It gives us a handle, a way to rewind the clock to those earliest days of our solar system, and that's why we're so fascinated by it. Launched on November 3, 1973, Mariner 10 was the last spacecraft of the program, but the first ever probe destined for Mercury. If you've got a means of getting a tremendous amount of information beyond your imagination at the present time. New areas of astrodynamics had to be invented to do this kind of thing. To reach Mercury, Mariner 10 was the first spacecraft to employ an interplanetary slingshot maneuver. Venus was the first to fly. It used the planet's gravity to decrease the size of its arc around the Sun, bending its flight path toward its target. You have to do your rocket burns at precisely the right time, alter your orbit in exactly the right amount, do course corrections, otherwise you can miss it. If not corrected, an error of only 1 mile at Venus could cause a 1,000-mile error at Mercury. Approaching Mercury, Mariner 10 began transmitting photographs of a world pocked with massive craters, revealing more clues to the formation of our solar system. These massive craters are evidence of early bombardment, so there was a period right after the solar system formed when many massive asteroids and comets bombarded the planets. Mariner 10 was the first spacecraft to return to its target, rendezvousing with Mercury 2 more times, to fly past the planet not once, twice, or 3 times. It helped us learn much more about this gravitational slingshot maneuver, which is essential to all the missions we use today across the solar system. So Mariner 10 was the cornerstone of every mission we fly today. Across its 3 encounters, Mariner 10 returned over 2,700 pictures of Mercury, revealing nearly half the planet's surface. Since March 1975, the spacecraft has slept soundly, still in orbit around the Sun. The next mission to the innermost world would take decades of preparation. Messenger arrived in Mercury's orbit in 2011 after a 6-year trip of 7.9 billion kilometers. Messenger was the first chance to put a spacecraft into long-term orbit around the planet Mercury to map its surface. The probe had to circle the Sun 15 times before it reached the exact speed and position to be captured by Mercury's gravity. We eventually viewed this planet, particularly Mercury's polar regions, areas where there are craters that have been in shadow for billions of years. We can see evidence of volcanism, tectonic deformation of these plains and ghost craters, which are impact craters covered by lava after they were made. The fantastic pictures of the planet's surface helped prove that Mercury is getting smaller. What we're talking about here is a phenomenon in the late stage of the evolution of planets. Planets were very hot in the past history of the solar system, and most of that heat still has a residue in the interior of the planets. Mercury's interior cools, shedding the heat generated during its initial formation. The surface is pulled inward, causing the planet to shrink. The surface is scarred, and we see those cracks and fault lines as the ground beneath the crust shrinks. This is a bizarre world, and one that is very much worthy of our attention. Messenger's mission came to a dramatic end in 2015. We want to end a mission in the most valuable scientific way. When the Messenger spacecraft ran out of fuel, it was sent on a last experiment, and that experiment was to basically self-immolate on the surface of Mercury. While we could study Mercury from orbit and make educated guesses about the density of the surface, the best way to do that is to smash the spacecraft into it. Closing in on the Mercury surface, Messenger collected data on the magnetic anomalies in the crust and ice hiding in the shadowed craters near the planet's poles. Mercury will not be alone for long. Bepi Colombo, a joint European and Japanese mission, has been spiraling toward the innermost planet. Launched in 2018, the missions are as wide open in terms of their capabilities as possible, because we need to know the right questions to ask of worlds that are as unknown as Mercury and Venus. That's what makes the exploration fun. Mars, a world half Earth's size, hangs as a red speck in our night sky. The outermost terrestrial planet, Mars's orbit lies 78 million kilometers beyond Earth's. As telescope technology improved in the 19th century, observers recorded fascinating shapes on the Martian surface. The sketches of Italian astronomer Giovanni Chaparral hinted at extraterrestrial architects. In the late 1800s, Zeffirelli made observations of Mars and drew maps of its surface, and some features that he saw he labeled canali, meaning channels in Italian. This created great excitement that we might have neighbors. We might go to Mars, and there would be other beings to talk to. In the 1960s, probes to the Red Planet sought to separate fact from science fiction. The fourth probe of the Mariner program became Mars's first visitor. Over a few hours, Mariner 4 captured 21 complete images and a partial 22nd, but each would take nearly 9 hours to transmit back to Earth. They had to wait so long for such a small amount of data. The figures cascade to the Earth. 240,000 bits of binary code, representing 40,000 dots that will finally make up the first picture. And waiting so long, they colored in the pictures with parcels because processing that data would take even longer, and they couldn't wait. What? The images did not reveal a world of extraterrestrial canals. When Mariner 4 gave us the flyby images of Mars, it revealed a desolate landscape. They saw dry rocks and craters and dust, and this differs from what they expected, and that may not have been very reassuring to the community then. We took for granted that the variation we see on the Earth would be found elsewhere, not realizing how unique water, and in particular life, are. However, Mariner 4's pictures were snapped in a brief flyby. A long trip to Mars might reveal more. The penultimate Mariner mission would confirm whether Mars was genuinely uninhabitable. The Mariner 9 probe was launched in May 1971. Mariner's rocket engine will be fired for 15 minutes slowing it by 3,500 miles per hour so it can go into orbit. Mariner 9 became the first spacecraft to orbit another planet. The probe's instruments unveiled the planet we know today. Over nearly a year, the two television cameras transmitted over 7,000 photographs to ensure that the entire Martian surface was mapped. An extraordinary world of two halves, the northern hemisphere almost perfectly flat, southern hemisphere heavily cratered, pockmarked, with highland regions and mountains. And there is this anomaly between them, what we call the Tharsis Rise. It is an area with vast amounts of volcanism in Mars's history. An enormous rift valley almost 3,000 miles long is an outstanding feature that no one expected on Mars. Mars has the highest mountain in the solar system, Olympus Mons, a giant volcano. It has dust storms. It has weather in its thinner atmosphere. So it really is a hectic world. We have fossilized riverbeds. Some mineral deposits can only form in seas and lakes. We have features that reveal global oceans. Mars has revealed itself to be a world with a past at least that was water-rich. Mariner 9 provided the first clues that waters once flowed on Mars. Humanity's first close-up examination of Mars would be facilitated by two identical craft, the Viking landers. They learned as much as they could about the surface of Mars given the technology. A small shovel on the end of a telescoping arm will scoop up some Martian soil, then drop it into a chemical analyzer on the Viking landing craft. Vikings 1 and 2 would touch down on opposite sides of the globe. The first photo from the Viking mission was of the lander's foot. That's a fascinating first image because it provides scientific information about the surface. The Viking landers did more than take pictures and measure the surface. They also did 3 experiments to look for life. The Viking spacecraft was looking to see whether there was any evidence of, for example, methanogenic microbes on Mars, microbes that would emit methane. Were there Martians? Was there some kind of life somewhere on the surface or below the surface of that world? Scientists concluded that the makeup of Mars's soil, coupled with solar ultraviolet radiation, restricted the formation of living organisms. But Viking's findings didn't exclude the possibility that an ancient Mars once supported life. We are still determining where we are in the evolutionary cycle. And, of course, that's part of what we're trying to find out with the Viking missions. They were simple landers sitting in 2 different locations in the 1970s. But if you really want to explore, you need that mobility. So we had a tiny little rover called Sojourner, which landed with the Pathfinder mission in 1997. It showed that we could operate a small automated vehicle on the surface of Mars, but again, it could only go so far afield. So they created 2 rovers by combining the lander and the rover into a single vehicle. The Mars exploration rovers were twin solar-powered robots designed to hunt for evidence that ancient Mars once held water. They were equipped with an entire laboratory to measure them, mineral content and other properties of samples that they could collect. It was just transformative to have that ability to have an automated human going around the planet. Spirit landed in a crater that had previously been filled with water. However, Mars has been covered by a layer of lava at some point in its history, so Spirit had to go on a much longer journey, traveling several kilometers to reach some mountains. And literally, when they got out of the lava field, they found what they coined the pot of gold, evidence that there was water in this spot billions of years ago. Spirit found rocks rich in iron and magnesium, which could only form when Mars was wet and warm. Spirit's twin successfully landed on the other side of the planet. The Opportunity rover, she landed in a small crater, the ultimate hole-in-one. And right in front of that rover was direct evidence that sedimentary layered rock materials can only form in the presence of long-standing water. The puzzle pieces have been falling into place. We have concluded that the rocks here were once soaked in liquid water. Spirit. She had to struggle for everything to achieve the goal of finding out the water history of Mars. It was all laid out in front of her as an opportunity. Initially slated for a 90-day mission, Spirit lasted over 6 years. Opportunity kept going for another 9 after that, traveling 45 kilometers further than any off-world rover. Opportunity made us Martians. A team of people goes to work operating in the rover, and the surface of Mars has now become our neighborhood. Mars can be both cruel and kind. They thought dust building up on the solar panels would eventually block the sunlight, ending their mission. But those whirlwinds on Mars blew the dust away, kept the solar panels clean, and allowed the rovers to drive further to continue doing more science. However, in 2018, a planet-wide dust storm sealed the Opportunity's fate. This dust storm, it was unfortunate. It actually was so huge, it covered the entire planet and lasted so long that Opportunity didn't have any power left. The rest of the instruments were working fine, but you can only do much else if you have power. The last message from rover Opportunity was from the engineering instruments on board, and effectively, it was, "My battery is getting low and it's getting dark." And so 15 years of operations on Mars's surface ended. This concludes operations for Merwin spacecraft ID-253, a sad day for all of us. Project off the net. Even without our rovers, humanity still closely watched the Red Planet. NASA designed the Mars Reconnaissance Orbiter, or MRO, as a next-generation eye in the sky, capturing surface features as small as a meter. It carried a novel telecommunication system that other Martian missions could use for navigational aid. Since its arrival in March 2006, the MRO has circled the planet over 60,000 times and sent back more data than all Mars missions combined. Its powerful camera has mapped 99% of the surface in unprecedented detail, revealing a planet that is still active and changing. The reason we know a lot about Earth is our satellites. We can measure what happens as a planet and how it changes, and that's what Mars Reconnaissance Orbiter has been doing for Mars. It's been measuring changes over the planet. Having a vehicle orbiting around Mars, like the Mars Reconnaissance Orbiter with its high-resolution cameras, has revealed the planet as an entire world with a diverse geology. In some ways, it resulted in better maps of Mars than we currently have of Earth. The MRO found interesting places where future landers and rovers could go to keep looking for water on Mars. While there was obvious evidence of there being water once on the surface of Mars, we'd never have gotten down there and dug it up and tasted it with the instruments of a spacecraft. The Phoenix mission landed near the Red Planet's northern polar regions and had a digger on board. That signal was detected, and just 6 centimeters below the surface, that came across this bright white material. The rovers have been investigating the history of past water on Mars for almost 5 years. Phoenix is the first mission to actually touch that Martian water. It tasted for the very first time the waters of Mars. Water is fundamental to human life. Knowing where the water is on Mars, how much there is, and how to access it is critically important for future missions. While water is an essential ingredient to life as we know it, our robotic Martian spies have detected a chemical often created by life: methane. The probes we've sent there have not yet found definitive evidence of life, but there have been some close calls. there have been some signals that complex organic chemicals might be there. We have tantalizing hints of methane on Mars. And why is this significant, at least on Earth? Methane is produced by living organisms. We call it a biosignature. It could be geological, but we may have found those first clues of life beyond the Earth. The hunt for life and other mysteries Mars still holds will continue with future missions. Where did the water go? Did it support life? Could it support life? Mars is an excellent example of all these big questions we have about the universe on our doorstep. And because it's on our doorstep, we can explore it more. And as we explore it more, like everything good in science, more questions arise. We continue to investigate Mars's past, hoping to learn more about its evolution from a primordial watery world. Our star bears some responsibility for comprehending the mechanics of the inner planets. We need to unlock the secrets that drive the solar system. We need to study the Sun. The Sun creates all the heat and light in the solar system, enabling all life on Earth to exist. It prevented life on Venus by causing the evaporation of all the water and turning it into a runaway greenhouse. It also created extreme environments in other terrestrial planets, preventing life in Mercury by stripping away its atmosphere. Our Sun produces weather, matter, and light, streaming out, influencing every orbiting body. Every so often, intense flares rise above the surface, ejecting charged particles up to 3 million meters per second. Sometimes these ejections collide with the Earth. When you see that beautiful aurora, the northern or southern lights, they are caused by solar storms leaving the Sun, hitting our Earth's magnetic field and rubbing it around. Now that's great. They are pretty pictures, but also create radio interference and problems here on Earth. The surge creates a geomagnetic storm that heats portions of the atmosphere and applies drag to satellites. It interferes with navigational systems and induces harmful electric currents in power grids. So, if we want to predict that solar weather, we need to understand how it originates and get up close and personal with it. Space-based missions have been trained on the Sun for decades, but until recently, they've kept their distance. The Sun. 3, 2, 1, 0. The mighty Delta IV heavy rocket lifts off with NASA's Parker Solar Probe, a daring mission to uncover the mysteries of our nearest star. Launched in 2018, the Parker Solar Probe will arrive within 6.2 million kilometers of the Sun's photosphere, what we describe as the surface. The Parker Solar Probe is ambitious because it will get just so close to the Sun, and that's going to be quite a hot place. And also, there's going to be a lot of radiation from the solar wind. Beyond the Earth's magnetic field, which directs most of the solar wind away from us, the Parker Solar Probe's instruments will have a shield of their own, 2 plates of carbon encasing a carbon foam core. On one side, temperatures will reach up to 1,400 degrees Celsius, but behind the shield, the bulk of the spacecraft will rest comfortably at 30 degrees. Incredibly, the spacecraft could make it through the trip, its instruments worked, and it could handle the heat from the front from the Sun. The Sun's temperature is one of the peculiar puzzles we seek to solve. It's a big mystery. You go to the Sun, the surface is 6,000 degrees Celsius. Move away, the temperature doesn't go down, as you might expect. The temperature goes up, and it goes up dramatically to 2 million degrees Celsius. How is the Sun actually doing that? We've got many theories, but the Parker Solar Probe will help us test those theories. It's essential for us to gain a greater understanding of solar activity and to monitor it. It'd be great if we could model it. The Sun is the engine of our solar system. The Parker Solar Probe will help us understand more about that engine and its workings. We'll get to lift the vehicle's hood for the first time. Mars is the closest within reach, but the challenges are many. Humanity has long aspired to become a spacefaring species, and the terrestrial planets may one day open a gateway to the universe. While it takes a few days to get to the Moon, Mars is an entirely different kettle of fish. A one-way trip to Mars would be roughly half a year, but a mission that brought humans back home would last 2 years. The biggest hurdle is how do we get people to Mars? We cannot solely rely on Elon Musk, never mind getting them on the surface. Those technical challenges are undoubtedly enormous, that's for sure, but we have an excellent history of overcoming that thing. The biggest challenges are going to be human challenges. Getting there emotionally healthy, physically healthy, that will be a significant stepping stone. The communication delays would be considerable. The delays in getting medical help would be considerable, so those colonies would have to be self-sufficient. Crewed exploration will require well-planned infrastructure already in place. We need to think about self-sustainable missions and use resources in situ, such as fuels and water from the planet, and use those to create the things we need to survive. Mars is a challenging place for humans to live on. Because there is no ozone layer on Mars, we would have to live underground due to the massive storms in the cold temperatures. The sun's rays come straight in, and that causes cancers and other terrible problems in humans. It has all kinds of hazards to do with radiation. Its atmospheric pressure is only about 1% of the Earth's. Its temperature is shallow. It would be a challenging place for humans to make a home. Laying the first bootprints on Mars will require our brightest minds. There's some fantastic innovation that needs to be done to solve this for things like the lunar mission. All these translatable devices, technology, and know-how benefit us back on Earth. We always get benefits by doing this kind of innovation and not being scared by these significant challenges. Before we set foot beyond Earth, we must answer a fundamental question. Are these worlds meant for us? It's a great philosophical discussion right now. We can colonize Mars in the future, whether we should or how we should do so. Humanity must explore, and with that comes a responsibility to the places we visit. For all we know, Mars might have living organisms on it. Until we can confidently say that Mars was utterly sterile, we must be careful how we treat Mars and not just look at it as a place where humans can take over. We should step lightly. The moment we step foot on an alien world, we have forever changed it. Unlocking the secrets of the inner planets, humankind learns more about our home. We look at Mars and Venus, our neighbors, and they are very similar to different times of the Earth, and that will give us clues about our history and destination. Even though the past 100 years of exploration have taught us a lot, we still need to keep pushing the limits. Explorers are who we are as human beings. We all do it from the moment we're born to the moment we die. With exploration, we advance as a civilization. The question is not whether we will enter these worlds, but when. It's in our nature to explore, understand, investigate, and be inspired by doing so.